Okay, so now we're going to talk about linear regression. Okay, linear regression is all about fitting a line to our data. So earlier we learned about correlation, fitting, or not correlate, not fitting. Just seeing if there's a relationship between two numeric variables. Linear regression says, okay, well, now that we've established a relationship between the variables, let's see if we can fit a line. Okay, so I'm going to just use the same data, the bedroom closet data that I've made up, and we've got 2, 6, 4, 8. Okay, and let's graph this again. Okay, so this is our data. 1, 2, 3, 4. Across the bottom, 2, 4, 6, 8 on the y-axis. Okay, and this is closets and bedrooms. And the way we have this set up is we are, based on the number of bedrooms, we are trying to make a prediction for closets. Make a prediction for closets. Okay, and so we want to create a line of fit. And the way this is going to look is it's going to be in the form y hat, our prediction for y, is equal to b0 plus b1x. Okay, b0 is our intercept, and b1 is our slope. Okay, and so the question is, what is the best fitting line? Okay, and so when you look at this, you might say, oh, you know what? The best fitting line is going to be this. Just pretend that's a straight line. Okay? It's hard to draw straight lines on this thing. Okay? And so in this case, that would have an equation of y hat is equal to 2x. Okay? Is this a good fitting line? Okay? Well, we need to, how good or how well does this data fit? Or does this line fit our data? That's what we want to know. Okay, so it seems like a reasonable line, having this, just imagine there's a straight line going through these data points. Y hat is equal to 2x. So we just say number of bedrooms you have, and you double that, that's going to be our prediction for how many closets you have. Okay. Well, how well does that fit the data that we have? Okay, so we have x and we have y. All right. So I'm going to introduce the concept of a residual. Okay, a residual is equal to the difference between the actual point and the predicted value for that point. Okay, so the residual is the actual value of y minus the predicted value of y. For that x, okay? Quote unquote, for that x, or in parentheses. So the residual is basically y minus y hat, and the symbol for residual is e. So let's look at this. Okay, so I'm going to create a column. Y hat is equal to 2x. These are our predictions. Actually, I'm going to use the color green. These are our predictions if we use this equation. So if y hat is 2x, our prediction here would be 2. Our prediction here would be 4. Our prediction here would be 6. And our prediction here would be 8. Okay. And so the residuals y minus y hat, here I have 0, 2, -2, and 0. Okay? Okay, and so there's different ways of evaluation, and in statistics we for some reason like to use squares, and actually the method we're learning today is called linear regression and also called ordinary least squares regression. Okay, so linear regression, also called ordinary least squares regression. Okay, and it's called least squares regression because we are trying to minimize the squares of the residuals. Okay. So if we look at our residuals, we're going to square them. Squared residuals. And so our squared residuals would be 0, 4, 4, and 0. Okay? And so the total squares of sum of the squares of the residuals, okay, so if I will be 8. 8 is my total sum of squared residuals. That's what I have. And so to illustrate this, here there is no residual. This data point is 2 units away from what was predicted, and this data point is 2 units below what was predicted, and so if we square them, this is what we have. Okay, so we have squared residuals, and the total area of these two squares is 8. That's what we've got. Okay. And so the question is there another line out there that does a better job of fitting our data? Meaning, is there another line out there that creates smaller sum of squares, okay, or smaller square area here? Okay. Is there a better fitting line? Okay. Well, the answer is yes, and I will show you that line. And I'll show you how you can find that line. Okay. So here is, I'm going to copy this, and I'm going to go to a new document. Alright, so this is the other one. I'm going to shrink this. Whoa. Okay, so the other one had sum of squares is equal to 8. This is y hat equal to 2x. All right, so here I'm going to propose this line. Y hat is equal to 1 plus 1.6 x. All right, so let's look at x, y, our y hat, our residual, and the squared residuals. Okay, so I got 1, 2, 3, 4, 2, 6, 4, 8. Okay, so if I plug in 1 into this equation, I would get 2.6. If I plug 2 into this equation, 2 times 1.6 is 3.2 plus 1 gives me 4.2. Over here, I have 5.8. And lastly, I have 7.4, I believe. Yes. Okay. So my residual here, y minus y hat, I have negative 0.6, I have 1.8, negative 1.8, and 0.6. And if I square these, I get 0.36. What is 1.8 squared? Something. 3.24. And if I add all of these up, my total sum of squares residuals is 7.2. Is that okay? The calculation of these sum of squares residuals? I will explain that, okay? But I just wanted to show you that this line, 1 plus 1.6x, which looks more like, let's see if there's another color here. I don't know. I'll have to do this color. Looks kind of more like this, okay? Has slightly different. All right, so the squares here, I'm gonna draw them over here. It's like impossible to draw. Okay. Well, this picture's terrible. Okay, but this blue line is a little bit of a better fit than the green line. Okay, the green line is not too bad. The sum of squares was 8, and this is actually the best fitting line with a sum of squares of 7.2, and you can't find a better straight line with a smaller sum of squares. Okay, but this is just to illustrate the idea of least squares regression. Okay, so the best fitting line at least according to ordinary least squares regression, is the line that produces the smallest total sum of squares residuals. Sum of squared residuals. Okay. And a residual, again, is the difference between the actual data point and the prediction of y for that value of x. Okay. I guess another helpful definition for residual is vertical distance between the data point and the prediction line. Okay, so that's the residual. And so we're looking to minimize the sum of squared residuals. All right, so how did I get this slope and intercept for the sum of squares residuals? Okay, so all least squares line, or all linear regression lines, will be in the form of b0 plus b1x, where b0 is the intercept and b1 is the slope. Okay, well, our data has the summary statistics x bar, standard deviation of x, y bar, standard deviation of y, and r. Okay, and so to get the slope, so step one, you find the slope first. Okay, so we can just thank other smart people who found that all least squares regression lines, the best fitting line, all have the same properties, in that the slope can be calculated this way. The r times the standard deviation of y divided by the standard deviation of x. Okay, that will be the slope. And the intercept will be y bar minus the slope b1 times x bar. Okay, and this is equal to the intercept b0. Okay. The best fit line always passes through the point x bar comma y bar. Okay, so if you take the mean of x and the mean of y and you put a point there, even if it's not an actual data point, the best fit line always passes through this location. Okay, so for example, with our bedroom closet fake data set, the average number of bedrooms was 2.5. There's no data point where there's 2.5 bedrooms. That's not possible. But the best fit line will pass through that point with 2.5 and 5 as the mean of x and the mean of y. So the best fit line always passes through this point, okay? And you'll notice that the slope of the line is the ratio between the standard deviation of y and the standard deviation of x, but quote-unquote tempered by the correlation coefficient r. Okay, and so the slope will never exceed will never be larger than standard deviation of y over the standard deviation of x. Okay, because correlation r is always between -1 and +1, so you will never have a slope larger than this. Okay, so this actually brings up a good point. What is the interpretation of the slope? Okay, so let's look at the our bedroom and closet data. We had y hat is equal to 1 plus 1.6 x, okay? Or y hat represents closets, so I could do closets hat. Predicted number of closets is equal to 1 plus 1.6 times bedrooms. Okay, so my slope is 1.6. What does it mean that my slope is 1.6? So remember, our line of best fit is we are predicting the number of closets based on the number of bedrooms. Okay? And so what this slope of 1.6 means is that if you were to observe two living places, and one place had one more bedroom than the other, then your prediction for that place would have 1.6 additional closets than the other. Okay, so your prediction basically increases by 1.6 every time you increase bedrooms by 1. Okay, so this our slope says our prediction for the number of closets increases by 1.6 if we increase the number of bedrooms by 1. Okay, and so the generic interpretation is the slope is the amount by which y is expected to change if x changes by 1. Okay. So if you increase x by 1, our prediction for y increases by the amount of the slope. Okay. I know in algebra they teach you slope is rise over run, but that's not very helpful. It just tells you how to put it on a piece of paper. But in terms of a real-life application, such as linear regression, the slope is how much you expect y to change when x changes by 1. All right, that's pretty good. Okay. Oh, we have to talk about the intercept. So we'll save that. Yes.
So you're saying with that equation, you will have the smallest squared residuals?
Yes. Yeah. So if you use, y hat is equal to b0 plus b1x, where b1 is equal to r s sub y s sub x, and b0 is equal to y bar minus b1 x bar. If you use this to determine your best fit line, you will have the smallest possible squared residuals that can be fit with a straight line. Okay, as far as straight lines go, this will be the best fitting line. And we're only going to learn linear regression, straight line regression. So just like many of the other topics in this course, you can go far deeper and learn much more detail about it. Linear regression is the most basic form of regression, and that's all we're going to cover in this class. There are more complicated forms of regression, which might be of interest to you as you go into your studies, but we won't get to cover that. Yes?
Is there a test statistic for the regression line to see if it's...
So we're going to just say if the correlation is significant, then the test, then this linear regression is good enough. Okay.
So we would use the same one
yeah.
we did earlier.
Yeah, and technically there could be a test statistic for the intercept, but yeah, we're not gonna worry about that. Okay. The test statistic for the slope is that correlation, the same one that we use for the correlation. That's the same. But technically there's one for the intercept, but we won't worry about that. Okay, so the intercept, the interpretation for the intercept b0 is y bar minus b1x bar. The interpretation for the intercept is that it is our prediction for y if x were to take on the value 0. prediction for y if the x variable has a value of 0. Now, it doesn't always make sense to plug in the value 0 for x, okay? So in our bedroom case, and the number of closets, we said closets, predicted number of closets is equal to 1 plus 1.6x. So can you have a place with 0 bedrooms? Nah, technically, yeah. You can have a studio apartment. I think that's 0 bedrooms. It counts as 0 bedrooms, I guess, in the scheme of things. And our prediction would be it would have 1 closet. Okay. Other things, though, you might try to predict the weight of a snake based on its length. Okay. And maybe you have a line of best fit. Can you have a snake with length 0? No. Okay, you cannot have a snake with length 0. So even if there were to be an intercept, it doesn't make sense. Okay. So in some cases, it doesn't make sense to plug in 0, but that would be the interpretation of the intercept. Okay, is that if you could plug in 0 for x, that would be the interpretation of the intercept. We have something called r squared. Okay. So if you take the correlation and you square it, at least for linear regression, it turns into big R squared, okay? And this is called the coefficient of determination. It's a fancy name for something not that complicated. Coefficient of determination, okay? And it is basically saying how much of the variation in y can be explained by x. Okay? So if you think back to ANOVA, okay, so last week we talked about ANOVA, and we said we have between group variation and within group variation. Okay, it's a similar concept here, except it's not between groups, it's just between different values of x. And so what we're saying is that, okay, you look at your data points, all of them have different values of y. Let's say you looked at a whole bunch of different living places and they all have different amounts of closets, okay? Or I mean, you see a large variation in the number of closets. Or you look at a bunch of snakes, there's a large variation in the weight, different weights that snakes weigh. We can just say, oh, well, everything's different and that's that. Okay, that would be the total variation in y. Okay, I'm sorry, how much of the variation, I gotta plug in y. Okay, that would just be the total variation in y. If we include the variable x as a way to explain the variation in y, maybe it can explain a lot. For the snakes, it can probably explain a lot. And you can say, well, longer snakes weigh more, shorter snakes weigh less. And if you take into account the length of a snake, there's probably not going to be a ton of variation left. Okay, if you look at all the snakes of length, 40 centimeters or whatever, there's probably not going to be a ton of variation from snake to snake regarding their weight. But if you look at something else, maybe where there is a lot of variation and the correlation is not very strong, maybe you want to try to explain someone's height versus their age. Okay. If you look at maybe you go to a high school, okay, and so you've got people of different age, and you're going to see some correlation between age and height. Okay, in a high school, you will see correlation between age and height. But if you look at all the students who are age 17, you're still going to see a wide variation in height. And if you look at all the students age 15, you will also see wide variation in height. Yes, there is correlation in that, in general, in high school, the 17-year-old students probably are a little bit taller than the 15-year-old students, and so on and so forth. But there's still a lot that goes into determining someone's height other than just that person's age. Okay, so the coefficient of determination is how much of the variation in y can be explained by x. So let's say if little r was 0.8, big R squared would be 0.8 squared, or 0.64. And that would go towards saying 64% of the variation in y can be explained by taking into account the x variable. Okay, so the other 36% in the variation can only be explained as individual differences. Okay, just like in ANOVA, you can say, sure, this is part of the reason why the lambs gained different weights. They were on different diets, so that explains part of the difference. But the remaining difference is just that they're individually different, so they're going to gain different weights. Same type of idea here. Okay, and that's that for R squared. I think that's pretty much it. You've got a few topics in the textbook that you can look over and do homework. So we'll see some of you guys on Saturday for the review. If you can't make it, don't worry. I'll record it and post it online. We'll see you guys next week for the final exam. Good luck as you guys study, and that will be it. Wish you guys all the best.